In last video, we have discussed about charging, compression, working and exhaust stroke. And in this video, I am going to derive expression for efficiency of Otto engine using PV diagram or indicator diagram. Okay, now let us draw the indicator diagram. That is, I am going to draw PV diagram. Here along y-axis I am going to take pressure, and along x-axis I am going to take volume. And here we can see that initial condition of this cylinder, that is, it is having volume V1, that is initially it is having volume V1 and pressure P1 and temperature, let us take it as a T0. That is, here I am going to represent it is having pressure P1 and volume V1. This is the point. And when a mixture of air and petrol is sucked by the cylinder, then we observe that the piston moves in downward direction and there is increase in its volume, that is V2, and also there is change in its temperature T1, but the pressure remains same, that is P1. And let us represent this charging stroke in PV diagram. That is, here there is increase in its volume but the pressure remains same. Here I am going to represent charging stroke by EA. Here temperature is T1. EA represents charging stroke. Okay, now let us represent compression stroke in PV diagram. Here in compression stroke, what happens? The piston moves in upward direction, and here we are going to observe that there is change in volume, that is, there is a decrease in its volume and there is increase in its pressure and also there is increase in its temperature. Here I am going to represent there is decrease in its volume but there is increase in its pressure. Here let us represent this compression stroke. Here we are going to observe that in PV diagram we represent adiabatic compression by A, B. Here there is change in volume and there is change in pressure, and one more thing, there is change in temperature and we denote the change in temperature by T2. And one more thing, at the end of the compression stroke the spark plug produces the spark, and because of this again there is increase in its temperature and there is increase in its pressure but the volume remains same, that is volume remains same, there is change in its pressure and there is change in its temperature but volume remains same at the end of the compression stroke, that we have already studied. And I am going to represent this by BC, and here temperature T3. BC represents combustion produced in the cylinder. Okay, this is about compression stroke. Okay, now let us represent working stroke in PV diagram. In working stroke, what we are going to observe, there is here the piston moves in downward direction and there is increase in its volume, and we take volume as a V2, and also there is decrease in its pressure and we take this pressure as a P3, and also there is decrease in its temperature. And I am going to represent this adiabatic expansion in a PV diagram. This is the CD represents adiabatic expansion which is produced in working stroke, and it is having the temperature T4, and we denote this process in PV diagram dA at the end of the working stroke. This is the condition. And here in exhaust stroke, what happens? This outlet valve is open. When the outlet valve is open, suddenly the temperature and pressure of the cylinder reduces and the volume remains same, and we represent this by dA. And when the waste gases completely passes through the outlet valve, then the piston moves in the upward direction, and we represent this by AE. And this is the PV diagram for the Otto engine. Here in PV diagram, EA represents the charging stroke and AB represents the adiabatic compression, and BC represents the at the end of compression stroke a combustion is produced, and because of this there is sudden increase in temperature and pressure in the system, and BC represents the combustion, and here CD represents the adiabatic expansion, that is in working stroke the piston moves in downward direction, and this CD represents the working stroke. After working stroke the outlet valve is open. Because of this there is sudden decrease in the temperature and pressure of the system, and we represent this by dA. And when the waste gases ejected from the cylinder, then the piston moves to the initial condition, and it is represented by the AE. Okay, this is all about a PV diagram. Okay, now let us derive expression for the efficiency of Otto engine. Okay, here in PV diagram at BC, this is the amount of heat energy Q1 is added to the system, and here Q2 is the amount of energy rejected by the system. First I am going to write a formula for the thermal efficiency is given by eta is equals to the amount of heat added to the cylinder minus the amount of heat rejected divided by amount of heat added to the cylinder. This is the formula for the thermal efficiency. Now what I'm going to do, I'm going to consider that we have added m kg of the working substance to the cylinder, that is considering m kg working substance. Here I am going to consider the air and petrol mixture added is m kg. Then here what I am going to do, let the amount of heat Q1 added at constant volume is given by, that is the amount of heat Q1 which is added at the constant volume is given by Q1 is equals to m CV delta T, and we have already discussed about specific heat capacity. Here I am going to use specific heat capacity equation, and here we are going to write the amount of heat added Q1 is equals to, where m is the mass, CV is the specific heat capacity at constant volume, and delta T is the temperature difference. Here the temperature difference is given by T3 minus T2, that is here we can write it as a m into CV T3 minus T2. This is the temperature difference. and this is the amount of heat added to the cylinder. Okay, now let us write the amount of heat which is rejected by the cylinder, that is the amount of heat Q2 rejected at constant volume is given by, it is Q2 is equals to M into Cv into delta T. Here also same, I am going to write the amount of heat rejected Q2 by specific heat capacity equation, and here temperature difference is given by T4 minus T1. Here I am going to write temperature difference T4 minus T1, and here I am going to denote Q1 by equation 1 and Q2 by equation 2. And in thermal efficiency equation we can write eta is equals to the amount of heat added. The amount of heat added is Q1, so Q1, the amount of heat rejected is Q2, and the amount of heat added is Q1. So we can write eta is equals to Q1 minus Q2 divided by Q1. And here we have calculated Q1 and Q2 value, and I am going to substitute these values in the above equation. Then we are going to get eta is equals to, here we can write it as a Q1 by Q1 is equals to 1 and minus Q2 by Q1. 1 minus Q2 divided by Q1. And here I am going to substitute Q2 value, that is M into Cv into T4 minus T1 divided by M into Cv T2 T3 minus T2. Here M into Cv gets cancel each other, and we are going to get 1 minus T4 minus T1 divided by T2 T3 minus T2. And let us denote this equation by 3. And here, since AB is the adiabatic compression, so we can write its equations, that is, since AB is adiabatic compression, so we can write its equation as a T1 V2 power gamma minus 1 is equals to T2 into V1 power gamma minus 1. This is the equation for the adiabatic compression. And similarly, let us write equation for the adiabatic expansion CD, that is, since CD is adiabatic expansion, and we can write equation for the adiabatic expansion, that is, here T4 V2 power gamma minus 1 is equals to T3 V1, that is here T3 V1 gamma minus 1. And let us denote this equation by 4 and adiabatic expansion by 5. And here I am going to subtract 5 minus 4. Then we are going to get T4, here T4 minus V2, here T1 minus V2. So here I am going to take V2 power gamma minus 1 common. So we get T4 minus T1 into V2 power gamma minus 1. Here we are going to get T3, here V1 power gamma minus 1 is common, so I'm going to take it as outside. Then we are going to get T3 minus T2 V1 power gamma minus 1, and we can write it as a T4 minus T1 divided by T3 minus T2 is equals to V1 gamma minus 1 V2 power gamma minus 1, or we can write it as a V1 divided by V2 power gamma minus 1. This is the T4 minus T1 divided by T3 minus T2 value. And from equation 3 I am going to write eta is equals to 1 minus V1 divided by V2 power gamma minus 1. And one more thing, V2 divided by V1 is the adiabatic compression ratio, and we denote adiabatic compression ratio by rho. So in place of V1 by V2 I am going to replace by rho. So we can write the expression for Otto engine is 1 minus, here I am going to write V1 numerator, that is V2 by V1, and this equation becomes 1 divided by rho power gamma minus 1, and this equation gives the expression for efficiency of Otto engine.